I'll introduce myself. So I'm Cedric Lescop. I'm working for Schneider. I'm based in Passy-sur-Eure, so I work for drives, working along with energy management, as I said earlier. So, why Zephyr and why we look at it? It was very first coming from an industrial need. So the need of flexibility via partial updates. As you know today, like in many products, when you want to update your products, you have to completely update it. It means you have to reflash the whole firmware. It can be very complicated. It can be very stressful because if you miss your hardware, if you miss your flash, if you don't have the second application, you can be just crashed. Depending on your protocols, on the way you do it, can be very, very hard to do it and to maintain. Our need was to do like to do basic ID was to do like on a mobile phone. When you have a mobile phone, you can add an application. You don't reflash your phone to do it. You just add apps and remove them. It was basically the ID, but this time with our business application. So quick look here, it was for where I work, for drives. We have a product in the middle, which is a soft starter ATS 490. Basically, we drive motors. That's a starter. So basically, this product just starts the motors and stops it with protection and stuff like that. But that's basically it. But we want to be able to add other applications on the field when a customer needs a new applications, like on your phones, if you want to add some coffee machines on your product. You could do that to it on the drive. And so what we look at in Zephyr, it was a new feature, which is called LLEXT. It's a subsystems. So I call it new now, but I think it was two years old now. So what does it do? Basically, what it does is that it takes some piece of code. So basically, use a ELF file. So ELF file is a really known format. I think it's executable and loadable format. So basically, when you build a firmware, you end up with a ELF file that you want to put on your device. The LLEXT is using the same format, but this time instead of refreshing your whole product, you just add the ELF file on top of your product, you load it, and you execute it on top of it. So you don't refresh anything, and you don't reboot anything, just load it and run it. How? When we start the proof of concept, we were using the very basic stuff, so it was only supporting a serial backend. So basically, you had to have your product connected to your host computer with a serial line, and you needed to stream your F, so the serial line, and then start execute it on your target. And doing so, you had to pass the whole instruction code because this new ELF file doesn't know where the other ELF file, where your base firmware is. Like if you're doing in a very simple example, there were at the very beginning there was only a sample which was the usual hello world, so it was calling printk. So if you send your extension on your product, you call printk on your extension, but it doesn't know where is the printk. So you have to basically parse the whole firmware and try to find where the printk is, and basically you patch it on the fly, and then you can execute it on top of it. What came along the LLEXT subsystem is, of course, a manager. There's a manager for everything in Zephyr. So when you send one extension, two extensions, you have to have some kind of manager which will ease your life. If you send two applications, you want to start the two applications, so you need to load the two applications or maybe unload them. You have to find the symbols. As I said, you have to look at the symbols to be able to parse them. And the other way around, if you want to find the printk, you have to find the printk inside the base firmware. So in Zephyr, the community implemented a manager to be able to give you also some easy to use for Zephyr. Like if you need some memory, like for the heap, if you need to do some memory allocation, everything kind of pre-done for you. You just need to use it. I won't go into too many details here. As I said, like LLEXT is using the Hell file. So thank you, NG Albertini, for your nice picture and your explanation. Hell file is basically like a huge shader at the beginning to say, okay, what's inside the Hell. Then you have different sections which are coded. Basically, you have your .data, your .bss, your .init, .no init, stuff like that. And then you have different headers because your section can be split into two other sections. You can do everything you want with this system. That's what's used Zephyr as for the base firmware, but it uses the same for the LLEXT feature. So I was talking about relocation and about the address. As I said, when you want to do a print key, when you do like some partial link with your new elf file for LLEXT, so the address of the print key is not there, so you have to parse it. So basically, you parse the firmware here. You see that the address is basically 0 plus an offset of 4, and so you have to find this code, and then you patch it. You have to add some ARM parsing code to catch it, modify it, and then you can be able to use it. So the key points of the relocation, LLEXT is very dependent on the architecture because, as I said, you have to parse the whole code, the whole code. So you have to find if you are on x86, you have to know which are the 886 instruction code to be able to patch them. Same for ARM v7, and same for Extensa. I think today the work has been done on Zephyr for ARM, and that has been done for Extensa as well. Not sure about the rest. Depending on how you link your new extension with the different compiler flags, if you use if you want to do a shell library, a static one, or relocation, or element calls, you won't have the same instruction, of course, in your codes. So there is a different way to find the opcode, to decode it, updating, and re-encode it, because of course you have to re-encode it to your architecture to be able to so the hardware is able to recognize it and execute it. There is also a different way to do it. If you don't want to actually parse the whole code because it can be very time consuming and takes a lot of time on your product to actually just load the application, you can use do some kind of it's like a partial link, and then you have to use a jump table. So basically your code is using a table. The table you don't know where it is yet, but then when your product starts, you just copy the table at some places and then patch it with the correct addresses. So your code which has been loaded knows the jump table and can use the new addresses. Not too many details, of course. I will stop there. So what we've done that's very exciting for Schneider Electric because we have innovation projects. We can do some proof of concept. You just need to find the money. When you have the money, you can start your proof of concept, build a team, and try to implement your idea. So what we've done, we used a board based on some Cortex M4. So we have afterwards different boards with an RAM. It works on any of them because Zephyr is working on any of them. So the purpose of the POC was to have the CAN stack as a complete extension. So basically, you send your product to your customer. Your product is not able to communicate on the CAN bus, and with some way you send the extension containing the complete CAN stack, and then your product without reflashing the product can talk on the CAN bus. So here you have a small example on the board with a button. What we've done is that we started two extensions. It was a very simple one, which was a counter. The extension was only incrementing a variable inside the base firmware, and we had the other extension, the CAN counter, on the CAN stack on the LLEXT, and then we were able to communicate with it on the CAN bus with the host. We have the CAN bus between both. The host was triggering a CAN connection and exchanging some frames on the CAN bus. And with this one, it was reading the variable which the counter was actually adding. So it was a +1, +1, +1 with an infinite for loop. And that way we could see that two different extensions had a way to communicate together. Even if they didn't know about each other, they were able to exchange some data with a variable. So it was a really nice concept on a product. What we did after we've done with the POC, when the money ran out, you have to stop. So you just look at the ideas. The ideas was is it able to do it with the XIP, the execute in place? So yes, it is, but you have to do some extra work there because you have to. Because before, when you load the extension, you load it into RAM, so you are able to, since it's in RAM, you can modify it. As I said, you parse it, decode it, re-encode it. But when you use zip, you are putting your extension into Flash, so you are no longer able to modify the code. So you have to find a way to maybe modify it before Flash it. So it's a complete different approach. Then we look at also the Zephyr user space. There you have a different constraint. I think you already talk about that. When you are in user space, you cannot say, okay, I want to call print k. Since you modify the code, you re-encode it to use print k, but then when you call it, you are not able to call print k because you are not allowed to call print k in the user space. It means if you want to use a user space in LLEXT, you have to take care about this kind of stuff. You have to give some authorization like you do on a mutex or semaphore on Zephyr, can grant some access. I think it's not done yet in LLEXT, but we have to work about that. And we had to do some measurement performance to see if actually having some code which is loaded has the same performances as the code which is not loaded, because if we have a drawback, it can be very bad. I brought the demo, but I won't show you the demo. You can do it afterwards if you want. Just here we have just add a picture. Can really read it. Just printing that we are actually able to load the both extension and successfully start the extension. So we know that we are counting and the stack is working. So to do continue the POC, we use we have to do some real-time analysis and validation. So we use different tools like MATLAB Simulink and Excel sheet. So basically we took so it's no longer a CAN stack. We took a simple application, like a business application, let's say, which was running on Simulink, and we built it and simulate with Simulink. So basically we took some inputs that we put on the board, and we recorded the outputs, and we do that on Simulink, and we do that on the board with the loaded code. And what there is that it's not two curves here; it's like 2 times 2 curves, because we have they are completely overlapped. The application is giving the same output based on the same inputs. It means that even if the code is loaded via LLEXT, it does exactly the same thing at the same time. So in terms of real time and in terms of behavior, it's exactly the same. So there is no drawback with the LLEXT subsystem. We push the investigation a bit further with some dedicated tools. We use the Percepio, and we use also system view. I'm sorry, I forgot to add the system view in the icon. And we did a lot of measurement with these tools like CPU load, time variations, synchronization, communication, etc., just to show that on LLEXT there is no modification on the performances at all. So it was really great about that. And close to the end now, and the impact on the product, which is very important for a product maker like us. The benefits. It's exactly what we wanted to do, that we can actually do some partial updates. We were able to send our application of the product and have the same performances. It's really nice because you can build your application a lot faster, because now, since it's a partial update, you just have to concentrate, focus on the LEXT extension and no longer on your base firmware extension. You don't have to validate everything from the start. You can say, okay, since my base firmware is the same, the validation is still okay. I just need to focus on the LLEXT extension and check out that I have no problem with that stuff. So you decrease a lot the piece of code that's changed, and you decrease a lot of the impact of it. So as an initial, we have to do what we call an impact analysis. We go much faster with LLEXT. But there is like drawbacks that the previous presenter said. With LLEXT, if you put some code onto your device, it means someone can actually tamper with your firmware. That's definitely not what you want. So you have to add some kind of security stuff with some private keys and secure keys to do like the previous speaker said, when you do like a trust firmware and you have to have a first a secure boot, a second boot, and then a secure application, then you have to find a way to have some secure extension. Okay. So last one is the credits for LLEXT was built with many REST people, so just thanks to all of them, and thank you to Tom Burdick, which from Intel will just let me copy his presentation and use it tonight. Thank you.